Hi, let's do some pH calculations of weak bases. Grab your calculators, you can follow along. If you're in my class, grab your Appendix 3, which has the KB values for different bases, and they're listed in this far right column. If you're not in my class, grab the OpenStax textbook, check online, and it's called Appendix I. And these are your constants for weak bases, all right? Now, oftentimes a word problem won't give you that constant, and you've got to kind of just look it up. All right, so first of all, let's understand the basic theory here. So weak bases, it's abbreviated as A minus, react with water, okay? When that happens, they grab a proton, right? And they transform to HA, which is the conjugate acid, and in the process they produce hydroxide ion. Weak bases produce a little bit of hydroxide, more than it's already present in water, and strong bases produce a whole lot of hydroxide ion, okay? So hydroxide ions are the defining characteristic of bases. They either have hydroxide in their formula, or they create it when they are added into water. All right, so the equilibrium expression here for this chemical equilibrium I have written out is products over reactants. And you want to write this on a note card, maybe have it handy on your desk or something, because this is the template we're going to use. So you've got HA and OH minus, which are products, so that's on the top of the fraction, and you have A minus on the bottom of the fraction. And H2O liquid is missing here because we don't use liquids in the equilibrium expressions. And so this is KEQ, just an ordinary equilibrium constant, but it's very special. It's used a lot for bases, so it's called KB. So B stands for base, and this is the base dissociation constant, all right? Now, the higher the KB, the more basic something is, okay? So if you have trimethylamine and ammonia, which are both bases, and one has a KB of 10 to the minus 5 and another has a KB of 10 to the minus 7, you've got to figure out, oh, the 10 to the minus 5 number is larger, so that's going to be the more basic substance, okay? All right, so here's the pH calculation overview. Yes, there are 5 steps, and I'll take you through this. You first want to write out the equilibrium. Again, on a note card is probably the template, so you know what to add to water to form what, to form hydroxide. Set up your ice box with those chemicals, solve for X, and then we want to calculate POH, and then at the end calculate pH. That's the overall goal here. All right, what is the pH of 0.04 molar sodium acetate? So what you want to do here is find acetate. I won't attempt to use the OpenStax one, but on Appendix 3, here's acetate. So if you go to the left, you'll find the chemical formula there under the base column, acetate, all right? It's C2H3O2 minus. If you add liquid water to that, it changes to acetic acid and OH minus, okay? So you need to memorize OH minus there, all right? And these are going to be the headers for our ice table, so there we go. And I've written initial change in equilibrium down the left-hand side of this ice box. And you want to go ahead and start populating the boxes. 0.04 is the only number we have, and that goes in the very upper left, and that triggers the whole process. On the right-hand side, we have 0 acetic acid in pure water, and we have approximately 0 hydroxide in pure water. I know there's minute amounts of hydroxide in pure water, but compared to the vast concentration excess of 0.04 molar, it's going to be assumed to be 0, and that's not going to introduce error. Once again, I put a little hyphen on the H2O because it's liquid, and it doesn't matter. We can just ignore water for the rest of this talk, all right? Now, where do we put the plus x's? We always put the plus x under the 0 because that's the direction the equilibrium has to go, and therefore we put minus x on the other side of the equilibrium right here. To get the equilibrium values, remember, you add those two columns, so 0.04 minus x and 0 plus x and 0 plus x, all right? So great, we have our equilibrium values now that we can use to plug into the equilibrium expression. So from our equilibrium, we can write down what the Kb is, products over reactants. In this very specific instance, we've got acetic acid and hydroxide in the numerator and acetate in the denominator, okay? And now we plug in the x and the 0.04 minus x, and here's where you get the Kb value, okay, for acetate. In my table, it actually says 5.6 times 10 to the minus 10, but that's probably a result off of some database online, all right? So now here's where you want to make the assumption. You see this equilibrium constant is very, very, very small. It's 10 to the minus 10th. That's just so teeny. So what that means is that this substance is going to ionize very little, and the 0.04 minus that very tiny bit is approximately equal to 0.04. So this is where we make that assumption to avoid having to use the quadratic formula, okay? I've never used the quadratic formula in all my years teaching chemistry because I always make these simplifications to make life simpler for my students. So let's do that today, all right? And what you'll want to do is combine the x and the x to get x squared, and then grab your calculator and for yourself verify that you're getting what I'm showing on the screen. Multiply by 0.04, okay? And I get something 10 to the minus 11. Don't forget to take the square root, okay? When you take the square root, then you get the 4.7 times 10 to the minus 6, okay? That's x. You might have to go back to the ICE table to figure out, well, what is x? X is the concentration of hydroxide. So we know hydroxide is equal to 4.7 times 10 to the minus 6 molar. Remember how I said x is tiny? That is tiny. If you take 0.04 and you subtract that tiny number, you're probably going to get 0.04 on your calculator. Now, what do we do with this hydroxide concentration? The next thing we want to do is calculate pOH. Remember, pOH is minus log of the hydroxide ion concentration. So we slap that in there, make sure you use that negative sign, and you get 5.33, okay? And that's the pOH. Next step, what you want to do is you want to calculate pH. And we use this awesome relationship here. pH plus pOH is equal to 14. That comes from the auto-ionization of water. And so what you want to do is now solve for pH, right? pH is 14 minus the pOH. And we just previously calculated the pOH, which was 5.33. So 14 minus 5.33 is 8.67, okay? At the very end, you want to do a reality check and think about things. So in this case, the pH is 8.67. Is that acidic or basic? You might have to pause and think, well, pH greater than 7 is basic, so this is a basic solution, and we're doing the pH of a weak base. So it makes sense. At least we're getting the pH in the right ballpark. If it was less than 7, it would mean the pH is acidic, and that can't be possible for a base, right? So that's it in a nutshell. Please check the description of this video, and I'll link another problem like this that I've worked. You'll need to do quite a few of these practice problems to kind of get a skill for it. Thanks for watching. Please like, please subscribe, and have a great day, everybody.